Let's imagine our radioactive sample as 100 unstable isotopes, each of which can decay by emitting radiation in order to become stable. So if we watch this sample decay, the first thing we notice is that the decay process is completely random. So we have no way of knowing when any particular particle will decay. As time goes on though, and more of them decay, the number of unstable particles remaining decreases. Because there are fewer particles left to decay, this means that the overall rate of decay, which remember is the activity, will also decrease. Which is why it looks like the sample is decaying more slowly than it was at the start. This is why we can define half-life as a halving of either the number of radioactive nuclei remaining, or a halving of the activity. They are both perfectly correlated, because fewer radioactive nuclei means a lower activity. Another way to show this decay process is by using a graph that plots activity in becquerels against time. As time goes on, the number of particles remaining and the activity of the sample will decline. But the rate of decline will also fall, which is why it's curved rather than a straight line. To calculate the half-life from a graph like this, we need to find the time it takes for the activity to halve. So in this case, drop from 600 to 300, which we can see is about 2 hours. And to confirm this, we could check another one by seeing how long it takes it to halve again down to 150. And indeed, it does take another 2 hours, so we can be confident that the half-life is 2 hours. If we had a different radioactive sample though, like this one, we can see that it's decaying much more quickly. This means that it started with a much higher activity, as we can see on our graph, and also that it will decline much more rapidly, and so a much shorter half-life, this time of 1 hour.